Hello everyone, welcome back on the series on DSP processor. In this presentation, I am going to explain you on ePWM time-based registers. Before going to start the presentation, I recommend you to subscribe the channel and press the bell icon for the latest update. The objective of this presentation is to get familiar with ePWM time-based module register, time-based control registers, time-based status registers, and at the end we will talk about these registers with the help of examples. The first thing, to initialize the time base for one of the ePWM, it is necessary to initialize the first group of registers. Now, how can we initialize the first group of registers? So these are the different kind of registers, time-based registers, like a time-based control register, time-based status register, time-based phase registers, time-based counter register, and time-based period registers. So how can we initialize these registers? These registers can be initialized in the program with the help of this structure ePWM1 ePWMX registers.tbctl.all. So it will initialize all the registers, all the bits in that registers. So like this structure, we can initialize each and every time-based registers in the program. The thing is, how to use these registers? So how to use these registers and how can we access these registers? So we can access these registers with the help of the source file as given by the Texas Instruments DSP2833X _ global variable definitions.c. Now, what is the purpose of this source file? The source file will define all the memory map registers as a global variables. Okay, while defining this source file, global variable definitions, this source file will define all the memory map registers as a global variables. Okay, now the thing is, all the variables are structure and union data type and already defined by the Texas Instrument. So we don't need to define all the variables again, and these are already defined by the Texas Instrument using the master header file that included in the master header file. It is given in DSP2833X _ header.h. For example, if you want to access the ePWM, so we have a total 6 ePWM unit, ePWM1 registers to ePWM6 registers. So the purpose of ePWM, this file defines the 6 structures. So this header file defines the structure of 6 PWM units, and which include all the registers that belongs to one of these hardware units. And now the thing is, if you want to access the period registers, so you can directly access the period registers. For example, if you want to define the period of 600 count pulse, so how can you define? You can define using the ePWM1 register.TBPRD equal to 6000. So this will define your period of the 6000 pulse using the ePWM1 registers. Now another thing is, you can for the controls registers such as a time-based control register, also you can define the full length of the registers. So how can you define the full length of the registers? Full length of the register you can define with the help of ePWM1 registers.tbctl.all. With the help of this all, you can define the full length of the registers. Now further, if you can think, if you don't want to define the full length of register and you want to assign the register with the help of bits. So for example, if I want to define the clock division, like in time-based control register, if I want to define the clock division, how can I define? In the bitwise manner. So in the bitwise manner, I can define ePWM1 registers.tbctl dot, instead of all, what can we write? We can write bit dot clock division equal to 7. Okay, so we will talk about in detail how to use this 7 and how to use this 1 2 3 4 in the examples. Okay, now the first thing is, we will talk about the time-based control registers. The time-based control register is the master unit of the ePWM unit. Okay, so it has a master unit and it is a 16-bit registers. So to access the 16-bit registers, first we will talk about upper 8-bit registers, and later we will talk about the lower 8-bit registers. So first is the upper registers are the upper 8-bit registers are phase shift registers, phase direction, clock division, and high-speed clock prescaler. So these are the upper 8-bit registers. So free soft is nothing but this is the emulator halt behavior. The free soft will control the interaction between the digital signal controller and the JTAG emulator. Like if it control the behavior in, suppose your DSP controller is connected to your system, your host PC, via the emulator. So it controls the behavior between the digital signal controller and your emulator, JTAG emulator. Now if the execution sequence of the code hits a breakpoint, we can specify what should happen to the ePWM unit, right? So how can we specify this? Suppose by using 00 to this bit, it means that you can stop the execution after the next counter increment or the decrement. If you are using 01, so when the execution should stop, it should stop when you are using count up mode, your counter will reach to the period, it should stop the execution. Count down mode, when counter will reach to the 0, it should stop the execution. And when it is up and down count mode, so when counter will be 0, it should stop the execution. And if you don't want to stop the execution, what can we write? You can write 1x, so it do not stop the execution. Now the phase direction. Phase direction is basically used for the synchronization of the 3 pulses. So what does it mean of the synchronization? So basically 2 hardware signals, synchronous inputs, okay, basically 2 hardware signals, synchronous input and synchronous output. These 2 hardware signals can be used to synchronize ePWM unit each other. It is used in a 3-phase control. So how can we synchronize? So in this case we have a one master unit, that is ePWM1. Okay, suppose we have one master unit, that is a ePWM1. This unit will generate the synchronous output signals. When it will generate the synchronous output signal? When counter equals to 0. When counter will equal to 0, it will generate the synchronous output signals. So what can we do with these signals when we generate the synchronous output signal? 2 more ePWM units are initialized to recognize these signals as a synchronous input signals and start counting immediately. So this is the way to stabilize the synchronization, right? So the phase direction will use using the it needs to be specified if the ePWM unit start counting up or counting down after a synchronization input pulse has been seen. If we are using single pulse PWM, okay, if you want to generate the single pulse PWM, single ePWM, so this feature will be disabled, so you don't need to take care of this phase direction, right? Now clock division. If you want to reduce the input clock frequency, so what can we do? You can reduce the clock frequency by dividing the input clock frequency by using these clock division bits and the high speed time based clock prescaler. So by using these two bit registers, you can divide your input clock frequency according to your desired frequency. So by using clock division 000001010, you can divide your clock frequency, and high speed clock prescaler, with the help of high speed clock prescaler, you can divide your input clock frequency. So this is the way you can divide your clock frequency, right? Now we will talk about the lower bit registers. The first register is the synchronous software for synchronization pulse. So an instruction that sets this bit will immediately produce a synchronous output pulse from this ePWM unit. So if you don't want any action, keep this bit as 0, and if you want a force one time synchronization, keep this bit as 1. Now is syncocell. Syncocell is selection of the source from the synchronous output signals. If you don't want to keep synchronization, if you don't want to keep the channel synchronization, switch off this feature. Now third one is a period load. Enable or disable. Enable means 0, disable means 1. So enable and disable the shadow register function of the TBPRD. If you are keeping this bit as 0 or 1, enable or disable, so it will enable or disable the shadow register function of the TBPRD. If you are disabling this by using 1, all write instruction to the TBPRD will directly change to the period registers, and if you are enabling it, a write instruction will store a new value in the shadow, with the next counter equal to 0, the shadow value will be loaded into TBPRD automatically, right? So when you are keeping it as 0, what will happen means you are enabling it, and when you are keeping it as 1, you are disabling it. So while enabling, a write instruction means the new value of the component registers will be stored in the shadow, and when next counter will be 0, the shadow value will be loaded into the TBPRD automatically, right? Now the third one is second one is phase enable. Enable 1, enable equals to 1, the preload the register TBCTR from TB time based phase by a synchronization input trigger. Okay, if you don't want to use it, make it disable, otherwise make it 1. Now counter mode. So we have a different operating modes. You can use a count up mode, you can use a countdown mode by selecting this bit is 0 1, and by selecting this bit as 1 0, you can use a count up and down mode, and by default it will be stop, it won't count, and it won't count up and count down, it will be freeze. Okay, so these are the time-based control register 16-bit registers. Now we will talk about the time-based status register. So this register flag the current status of the ePWM unit. So this register bit will show you the what is the current status of your ePWM unit. So how it will be, the counter direction. So this counter direction bit will indicate whether it is counting up or it is counting down. So when it is counting up, it will this bit will show 1, and when it is counting down, this bit will be showed as 0, right? Now the second one is synchronous input. So this is if the synchronous input event has been seen by the PWM unit, this bit will be 1. If it is not, it will be 0. For example, if the synchronous input signals event has been seen by the ePWM unit, this bit will be 1, otherwise this bit will be 0. And the next thing is to clear this bit we must write a 1 into 8, right? Now the last one is the counter maximum. So this is the counter maximum. If some reason a 16-bit counter TBCTR overflows, for example, if due to some reason our time-based counter overflows, this is the 16-bit or it overflows, the counter maximum bit will be set to 1. In this case, the counter maximum bit will be set to 1. Okay, so under normal circumstances, this should be happens. So we can treat this bit as a security alert signal. Okay, so under normal condition, this should not happen. So we can treat this bit as a security alert. So now to clear this bit, we must write 1 into this register, into this bit. So these are the time-based status registers. Now till now whatever we have discussed, we will use that information and we will generate a 1 kHz signal using the ePWM 1A. So to generate the 1 kHz signals using the ePWM 1A, what time-based registers we need? We need a different kind of time-based registers. First one is, okay, what information we want from the time-based registers and what are the registers involved. So first registers will be define the signal frequency. Okay, so we need to define the signal frequency. The second thing, we need to define the operating mode. What is the operating mode and what is the time prescale. Okay, the third one is we need to define the signal shape. What should be the signal shape? So the signal frequency is defined by the TBPRD, time based period register. Operating mode and time prescale is defined by the time based control register, and the shape of the signals will be defined with the help of action qualifier. Okay, so these are the registers involved by defining the to generate the 1 kHz signals using the ePWM 1A. Now first thing, we need to define the signal frequency. So signal frequency is defined with the TBPRD value. So how to calculate the TBPRD value? So here we are using the operating mode is up down mode, not up mode, not down mode. We are using up down mode. This mode we are using. So TBPRD value will be defined as 1 by 2 into PWM time period divided by system clock output into clock division into high speed prescaler clock division. So we know the system clock frequency is frequency is 150 megahertz and PWM frequency is 1 kilohertz. So your task is to generate the calculate the TBPRD value where the system frequency is 150 megahertz and the PWM frequency is 1 kilohertz. So by appropriate choice of the clock division and high speed clock division, you can find out the value of TBPRD. Okay, so and one thing you must keep in mind that TBPRD is a 16-bit register. So the value of the TBPRD should not exceed more than 2 to the power 16 minus 1. So you should keep in mind that the TBPRD value should not exceed more than 2 to the power 16 minus 1. So that is equals to 65,535. So TBPRD value should not exceed beyond the 65,535. Now your task is to calculate the TBPRD value by appropriate selecting the clock division and high speed clock division. Okay. So you can pause the video here and just calculate the value of TBPRD and comment me on a comment section, right? So the first thing, we need to initialize the GPIO pins and as a ePWM unit. So initially what we have done, we initialize all the GPIO pins from 0 to 15 bit as a GPIO pin, and later we use the GPIO 0 equals to 1, that is ePWM 1 will be activated, right? And the next thing is we calculate the appropriate value of the clock division and high speed clock division, and the counter mode is 2 for the up down mode, and the action qualifier is 0x0006. So what we have done using the action qualifier, so this is the up down mode. So you want to generate the 50% duty ratio. Okay, when your signal will be at 0, your action should be set means it will be 1. When it will reach the period, okay, when it reaches the period, it should be clear. So it will generate the pulse of the 50% duty ratio, right? This. Okay, and by selecting the value of the TBPRD, by selecting value of the clock division and high speed clock division, your TBPRD value is 37,500. Based on this calculation, you can get a PWM pulse of 1 kilohertz frequency with 50% duty ratio. You can try this with a Code Composer Studio, and I'll also make the videos on how can we do with the Code Composer Studio in the real time. So in the next lecture, what we are going to cover, we are going to cover the pulse width modulation scheme by using the extra registers like compare register. We will do the comparison of the registers, and we will talk about the action qualifiers. Okay, if you have any query, you can comment me on the comment section. I'll try to solve all your queries, and please like, share and subscribe my channel. Thank you very much.